Hi Lauren, so here's my HPLC concept map. I'll quickly zoom into the legend, and if you'd like you can pause it here and have a read through that, but I'll try not to waste too much time going through what's there. So at the top of my concept map, or the highest level, I've got all these crowns, which are the royal family members, and at the very top I've got resolution, which I think is essentially the main aim or the key goal of HPLC, and that's why it's the biggest and in the middle. And then underneath that I've got peak tailing, runtime, back pressure and sensitivity as the other royal family members. The next level are these red circles, which are the calculator responses, and they're also the components that make up the resolution equation. So we've got retention factor, selectivity, and efficiency. So the gradient retention factor over here is a little bit different, and it's more of a theoretical notion, whereas the isocratic retention factor is pretty much the ratio of the time spent in the stationary phase over the mobile phase, or the concentration in each phase. Selectivity is the ability for this to chemically distinguish between two sample components, and then the efficiency is the dispersion of the analyte bands as they travel through the HPLC. I've also got the HEPT, or the Van Deemter equation here underneath efficiency there. The next level is the responses. So in the blue boxes with the yellow tick, these are things that we can read directly off a chromatogram. So I've got the T0, the retention time of uracil, retention time of our other analytes, then the height, the width, and the area under the curve for each of the peaks. On the bottom level here, I've got the different parameters. So a droplet or a drop of liquid, or whatever you want to think that is a chemical parameter. This computer screen here is a mechanical parameter. A star means it's neither chemical nor mechanical, and then temperature here indicates that it's both chemical and mechanical. Each text color inside the different symbols has a different meaning. So we've got green, which is a mobile phase parameter, orange, which is a column parameter, blue is equipment, and then red is sample. And here, these two red boxes, I've got them between responses and parameters, simply because they're kind of in between. So viscosity and linear velocity are what we call indirect parameters. So they're things that we can control, but not necessarily directly. Due to the time constraints, I'm just going to speak about the main links that influence each of our royal family members. So I'll start with resolution, because as I said, that's the most important. So the way we influence resolution is through these three components here. So our main links are the ones in red here. So the main parameter that we can use to change K, or retention factor, is percentage B. So as we decrease percentage B, we increase percentage A. As we increase percentage A, we increase the polarity of the mobile phase, which increases the repulsion of the analytes into the stationary phase, so that increases retention. And as uracil is not retained at all, increasing the polarity will not affect its retention, as it completely stays in the mobile phase regardless of the polarity. So TR is changing disproportionately to T0, so then therefore we get a change in K. The main parameter that we use to change selectivity is from this red line here, so it's a little bit confusing, but if you follow it down, it comes from the different solvent type. So different solvent types are the main parameter we use to change selectivity, and the reason we do that is because all the different analytes will have a different affinity for different mobile phases. So some may increase in retention time, some may decrease, and we also may see some increase more than others, or some decrease more than others. So then we get a disproportional change in the K values, and that is ends up being a change in selectivity. The polarity of the different mobile phases does play a role, but it also involves other things, such as the acidic, the basic, and the dipolar nature of each of the different solvents. The main factors that affect efficiency are linear velocity, and that can be controlled by both diameter and flow rate. Diameter, if you think about a hose, if we squeeze the hose, we decrease the diameter, we increase how quickly the water comes out of the hose, so that's an increase in linear velocity. And flow rate's, I guess, the same as turning on the tap a little bit more. So you turn on the tap a little bit more water comes out, and it also comes out faster. Linear velocity actually affects longitudinal diffusion inversely, and mass transfer directly. Another parameter that we can use to change efficiency is the particle size, which affects eddy diffusion, which has to do with the path that the molecules or the analytes take through the column. So if we have smaller particle sizes, we have less eddy diffusion. And then lastly, pore size also affects C, so mass transfer, which means, I guess, if we have bigger pores, it means some of the molecules can get trapped deeper within the pore, and that causes the molecules to spread out a little bit more, and we get more band broadening. So they're the main influences main parameters, that affect these three, which then affect resolution. The other things we have, obviously, we'll start off with peak tailing. So so we've got end capping here, ligand density, and the type of the ligand, which is a little bit hard to see, but hopefully you can zoom in on the Prezi link that I send. But basically those three influence peak tailing by affecting the accessibility or the access of the analytes to the silanols. So if we have more end capping, there's obviously less silanols available. If we have a greater ligand density, again, there's less silanols available. And if we have a longer ligand, we have more steric hindrance, so the analytes can't be attracted or interact with those lone silanols, and we don't get the lagging of some molecules from the bulk and peak tailing. The other ones we have are the silica metal content, so the metal acts as chelating agents, and if we have more of those, then obviously there's more peak tailing. And then lastly we have pH, and pH influences peak tailing because it can activate or not activate the lone silanol, so that influences the amount of peak tailing we have. The parameters that we have that affect runtime are mainly to do with linear velocity, I guess, because if we think about the speed at which the analytes travel at, has a great influence on what time they elute. So if they travel faster, they obviously elute quicker, and if they travel slower, they obviously elute a lot slower. And if the last one elutes quicker, then it's obviously a shorter runtime. Other things that influence runtime are length. If the analytes have a further distance to travel, it obviously take them a longer time. We also have back pressure. Back pressure is influenced a lot by viscosity. If we have a more viscous mobile phase, then we obviously have to push it harder, and that hard pushing is a higher pressure. Length is also important in back pressure, because if we have to push that liquid a further distance, we always have to push it a little bit harder. And then diameter as well. I mean, if we decrease the area or the space for the liquid to move through, you have to push it harder to get it through that smaller space. And then flow rate as well. If we turn that tap up more, if we have more liquid to push through the same size column at the same rate, we obviously have to push it harder to get all that extra liquid through. And particle size is also important. If we think about a tube full of little grains of sand or filled with pebbles, we always have to push through the grains of sand a lot harder because there's less space through there and it's a lot tighter. So that's why particle influences back pressure. And lastly, we have sensitivity, which is essentially the height of the peaks. One of the parameters that influences that massively is flow rate, and this is through the area under the curve, because the detector is absorbance per unit time. So if the flow rate is lower, we get a large increase in height. And also wavelength as well, through its influence on area under the curve. If we have the right wavelength, we get a much bigger peaks and greater height and sensitivity. And also retention time. As the peaks stay in the column longer, they become shorter and wider, and that has an influence on height. So hopefully, I didn't have the time to go through everything, but hopefully all these links make enough sense that you didn't get lost going through the version of the Prezi. And thank you for all your help and all your feedback with this.